Welcome everyone. I've always been interested in alkali metal in our food, particularly potassium. The website with the dietary guidelines provide a great resource on this, showing a whole list of different vegetables and their specific potassium levels. Among them, one that really stands out is potato. According to their chart, a single medium-sized baked potato with skin on contains an impressive 926 milligrams of potassium. So in this video, I'm gonna extract pure potassium metal from potatoes, step by step. Enjoy this experiment. I have here 40 grams of fresh potatoes. I will cut it into small pieces and let it dry in the sunlight. After several weeks of drying, the potatoes lost approximately 80% of their initial weight. After removing the majority of the water, I will work to eliminate the remaining moisture completely. This pyrolysis process is designed to thermally decompose the organic component of the potatoes, resulting in the formation of residual ash and charcoal. During the process, volatile compounds are released, like aldehyde and methane gas, reflecting the mineral content of the original potatoes material. After complete drying, the charcoal will be combusted to produce ash. The resulting ash is predominantly composed of potassium carbonate. I will dissolve the ash in approximately half a liter of hot distilled water. The precise volume of water is not critical, as potassium carbonate exhibits high solubility. This allows for efficient extraction of the soluble potassium salt from the inorganic residue. Now I will just filter the ash to obtain a solution rich in potassium carbonate. I've used this process twice with hot water to get maximum amount. I will now prepare a lime solution. Lime is calcium oxide. When added to water, it reacts immediately to form calcium hydroxide, which is slightly soluble at room temperature, about 1.7 gram per liter, will dissolve. This limited amount of dissolved ions will then react with the potassium carbonate. And this is how potassium hydroxide produced. This double displacement reaction with precipitate explains everything happening in this experiment. Once I done, I filtered it very well from calcium carbonate and dissolved lime powder. I thought some calcium hydroxide still dissolved, but I wouldn't worry about it. Now I just dry the solution. Here I've got 12 grams of solid potassium hydroxide. I will work now to make a simple alkaline metal converter. I set out to make a metal tube, sealed on one end and openable on other, for which I used the galvanized tube. However, I made a mistake. It would have been better to remove the galvanization layer using hydrochloric acid. This negatively affects the quality of welding, and moreover, the zinc reacts with materials I was working with. As is well known, zinc is a highly reactive element that can interact with other substances under certain conditions. This experiment requires pure aluminum metal, so I have obtained it from aluminum cans. Well, after preparing the aluminum, now let's jump to the interesting part. I will mix potassium hydroxide with aluminum. But before I do this process, I will work to remove the majority of the moisture in potassium hydroxide. And remember, the important step for the success of this process is removing the moisture in the potassium hydroxide. Potassium hydroxide is highly volatile when heated and produces toxic, shocking fumes. You must wear protective masks, gloves, and follow safety precautions in a well-ventilated area. The hydroxide was placed on the bottom and aluminum on top in order to prevent an immediate reaction, as the hydroxide still contained a small amount of residual water. I will add aluminum in excess to ensure that all the hydroxide reacts and is consumed. If you want to add the material precisely and truly understand how the reaction takes place, everything starts from the chemical equation. This equation tells us we need a molar ratio of 6 moles of potassium hydroxide for every 4 moles of aluminum. Let's break down the exact number for our experiment. We are starting with 12 grams of potassium hydroxide, which calculate to 0.21 moles. Based on 6 to 4 ratio, this requires 0.14 moles of aluminum, which has a mass of 3.85 grams. In the first stage, aluminum reacts with potassium hydroxide, the presence of moisture, releasing hydrogen gas and forming potassium aluminate. Soon, as the water evaporates and once the required temperature is reached, the deep reduction process might begin. After 5 minutes of strong heating, the hydrogen now is being released vigorously, and once the water is consumed, the vigorous production of the hydrogen will stop. The process occurring inside the tube can be represented by the following chemical equation. I spent around 50 minutes heating with a strong flame, thinking that nothing would happen, only gas being released. After a while, you can observe hydrogen being released vigorously again, indicating the onset of the reduction process. This can be represented by another reaction equation, which constitutes the key process in this video. At high temperatures, it's assumed that aluminum reduced the potassium ions from potassium hydroxide to metallic potassium. Since potassium has a relatively low boiling point, 7600 degrees, it will evaporate at such elevated temperature. And along with the hydrogen gas, potassium vapor is released. Therefore, I placed silicone oil at the outlet of the tube, so that the potassium would collect the oil as it exits. Silicone oil is regarded as one of the best mineral oils, as it withstands the high temperature and does not react with alkaline metal. My alkaline metal converter crashed due to the high temperature, which reached 1000 degrees. The silicone oil became extremely hot, which led to the dissolution of the metal on it. But a large part of it was stuck in the tube outlet because of the cold outlet, where it accumulated. A little heating made it drop into the oil. Okay, this is all I got. I will wait it now. It could have been possible to obtain a much higher amount, but a large part of the potassium carbonate did not burn well, and also during the reduction process, my alkaline metal converter cracked, which stopped the reaction, but this is still good. Potassium metal is characterized by being soft and ignite immediately with contact with water, with a purple flame. Okay, the remnant in the tube, some potassium aluminate, along with a bit of aluminum metal that I've added with excess, and a particle of potassium metal that hadn't yet evaporated.